Welcome to our webcast, Industrial Ethernet Part 1, Technologies. Now I'm happy to introduce today's distinguished speaker. Mike Robbins is a Network Engineering Manager at Tricor Incorporated with over 24 years of IT industry experience. Robbins oversees the design and implementation of industrial Ethernet networks for a diverse mix of Tricor customers. He's focused his career on IT networking during the past 15 years and earned a Certified Network Administrator certification in 2002. Robbins also has been involved in industrial networking for more than 5 years, including as a Senior Field Network Engineer for an industrial Ethernet switch manufacturer. Tricor is a system integration firm based in Racine, Wisconsin. I'm Mark T. Hosky, webcast moderator today and content manager for Control Engineering since 1994. I will be presenting some industrial Ethernet survey results. And now Mike Robbins from Tricor.
Thanks, Mark. I'm going to cover the Ethernet technologies that have the most impact on the performance of your industrial Ethernet network. We will point out the standard to follow for a good network foundation because the most difficult and expensive network infrastructure to change is the cabling. We will also talk about a couple of Ethernet features, namely Igmp Snooping and Vlans, that you might require on your switches. Then we will talk about networking technologies after that. Let's start with the cabling. The TIA, which is the Telecommunications Industry Association, created the TIA-568 standard that defines the categories of communications cabling. The cable manufacturers are required to adhere to this standard to make sure these specifications are met. These categories are how we can easily identify the type of cable we need for a specific enterprise application. Notice I said enterprise application. I didn't say industrial application. So to start with, at the top of this list, we have Category 1, which was originally used for analog voice communication. Category 3 cabling is the level that 10 megabit per second Ethernet moved from coaxial cable to twisted pair cabling. It could be used in lengths up to 100 meters before a repeater was required. Category 3 is now commonly used for analog voice applications. Category 5 was designed for 100 megabit per second Ethernet, but has since been superseded by Cat5e. And Cat5e is also limited to 100 meters. So the E of Category E means enhanced. The enhancement over Cat5 cabling is to support gigabit speeds. Until the last few years, this was the most commonly installed category of cable. Category 6 supports 1 gigabit speed up to a distance of 100 meters, and it also supports 10 gigabit Ethernet, but only to 55 meters. And then there's Category 6A, or Augmented Category 6. And this category was developed because it is required for 10 gigabit speed for that distance over 55 meters that Category 6 couldn't cover. This category improved what is called alien crosstalk. It's a strange term, but alien crosstalk is caused by the 10 gigabit signal having creating such a large electromagnetic field that it affects the cables running parallel to it if they are tightly bundled together. That is why if you are using 10 gigabit Ethernet, you must use Category 6A cable. Let's define a few cabling terms before we move on. Fixed or horizontal cabling uses solid conductors and should not exceed a maximum length of 90 meters when accounting for patch cables on both ends. The length is measured between active devices like switches. Patch cables use stranded conductors, which offers more flexibility but also has more attenuation than the solid conductors. That is why the lengths are limited to 10 meters for patch cables. The combination of a fixed cable, patch cables, and connectors and patch panels are all called the Ethernet channel. The Ethernet channel for 100 megabit, 1 gigabit, or 10 gigabit should not exceed 100 meters in length between active devices. So what happens if you exceed 100 meters? Any of these Ethernet channels over the standards defined distance will not pass certification. On a more practical note, there can be a high rate of packet loss due to errors, and identifying cable length problems can really be difficult to track down. Let's take a closer look at the three most widely used copper cable categories for Ethernet networks. Category 5E uses individual wires that are 24 gauge for fixed cabling and 26 gauge for patch cables. Category 6 has thicker conductors than Category 5E. They are 23 gauge wires, which has less signal attenuation and as a result is better suited for industrial applications. These thicker conductors also make it a better choice for PoE or Power over Ethernet applications than it does for Cat 5e. Cat 6, like I mentioned before, also supports 1 gigabit maximum speed up to 100 meters. Now, Cat 6a cable is required for 10 gigabit speed connections over 55 meters in length and up to 100 meters. Although 10 gigabit is rare in an industrial network, in fact, very few PLCs and VFDs have an Ethernet interface faster than 100 megabit per second. The 10 gigabit signal speeds cause excessive crosstalk that the twisting of the pairs within the cable itself cannot overcome. So early Cat 6a cables used a center spline to curtail the crosstalk between the pairs, which also creates a thicker overall cable. But lately, the higher quality cable manufacturers have since refined that design so that the newer Cat 6a cables, they don't need that center spline anymore. The Telecommunications Industry Association has a standard for commercial environments, which is the TIA 568. It's called Commercial Building Telecommunications Cabling Standard. The standard, which was ratified in 1991, is to provide the recommended practices for the design and installation of Ethernet cabling systems. Before this standard, there were an increasing number of proprietary network cabling systems that were increasingly expensive. The backbone of this standard defines the topology, media, and maximum cable distances allowed. When they talk about media, they talk about both copper and fiber media. The cords and jumpers are also defined, and it is stressed that the patch cables be of the same or better category than the backbone cable. In other words, if you installed Cat 6a cable, make sure that you use Cat 6a patch cables to go with it. The standard also defines the horizontal cabling and stranded patch cables in terms of wire gauges, impedance, and crosstalk between the pairs. Stranded patch cables are for short runs and have more flexibility than horizontal cables, though they should not be terminated out in the field with RJ45N since they are stranded. Since this standard, the TIA 568, is intended for office environments, how does that apply to our industrial environment? In response to the greater use of Ethernet in industrial networks, in 2009, the TIA ratified the 1005 standard for industrial infrastructure to provide the recommended practices for industrial Ethernet networks. In contrast to the TIA 568 standard, which addresses commercial buildings, the central concept of the 1005 standard is the potential exposure to the hostile environments of industrial applications. A prime design principle of the standard is the special cabling system requirements for some industrial applications, such as cables used for IP67 connectors, which use 2 pairs of wires instead of the standard Ethernet 4 pairs. It also allows for the use of stranded wire patch cables at longer distances than defined in the 568 standard. The standard also states that Category 6 or better cabling should be used even if those PLCs, drives, or HMIs may only have a 10 or 100 megabit per second Ethernet port. Remember, 100 megabit per second Ethernet only requires Cat5e according to the TIA 568 standard. So what else does the TIA 1005 standard define? Well, it defines 4 environmental categories that can affect the Ethernet infrastructure. There are 4 classes that make up this new acronym that we're going to put out there, and that's the MICE acronym. The M stands for mechanical, which is bending, flex, crush, or impact for the cabling or infrastructure. Ingress of particulates or liquids. Climatic and chemicals for ambient temperature, humidity, detergents. And electromagnetic, whether radiated or conducted RF, and also electrostatic discharge and surge. One of the basic takeaways from this standard is the reasons for using a particular category of cable. In a commercial environment, the category of cable would be chosen to support the highest bandwidth devices on a network. Most desktops and laptops are at 1 gigabit per second, and servers are typically at 1 gigabit up to 10 gigabits per second. The cable of choice would be Cat6a for current and future bandwidth support in this instance. In contrast, most industrial Ethernet networks have devices that range from 10 megabits per second to 100 megabits per second, and which would only require the need for Cat5e cable according to the TIA 568 standard. However, the TIA 1005 industrial standard states that at least, or use at least Category 6 cable should be used in harsh industrial environments. Let's take a look at the 4 basic types of industrial areas and how it might apply to this new MICE acronym that we talked about. So at the top we have a telecommunications room. This might be a MICE 1 or really a commercial grade type of cabling. And then we have the factory floor. Typically it ranges from MICE 1 to MICE 2, which is commercial grade to light industrial. And then there's a work area. It may range from commercial grade up to light industrial, which would be a MICE 2 or MICE 3. And then an automation island, which is typically exposed to the harshest environment, which we would typically do or recognize that as a MICE 3. A higher MICE level means that your physical infrastructure may need to be ruggedized for vibration, sealed for washdown, fabricated with materials that can withstand extreme temperatures, and shielded for rejecting EMI noise. There are white papers that will explain the standard in detail. Ask your cabling contractor what standard they will use to cable your new machines to your Ethernet switches. Hopefully they will answer TIA 1005. What standards don't do is define how to avoid the cabling mess you see in this example. Make sure to include cable management when ordering racks for SCADA systems or plant floor panels. Use different color patch cables for specific categories of devices or for different networks. It is up to you how to color code. There is no specific standard for that. Do not connect solid wire cables directly to end devices. They need to be terminated in patch panels, even patch panels inside control panels. Then use factory-terminated and tested patch cables from the patch panel itself to the device. Make sure to label it and use a naming scheme that is logical for your network. And finally, document your network. It speeds up troubleshooting your network for you and also for any outside assistance you might need for your network. This is an example of a typical network diagram. During our discovery process of this particular network, we found that the 3 main switches did not have a redundant connection. You can see this in the IDF1 location at the top center of the drawing. We simply added a cable between the two switches to provide redundancy. Since we don't change our networks that often, we can easily forget the details that we will need in the future for troubleshooting or network expansion. So what is the role of your industrial network? When deciding what type of Ethernet switch to select for your industrial Ethernet network, the systems on your network will tell you what Ethernet features are required. If the devices on your network are controlled by a proprietary network, but the data itself is collected through an Ethernet network, then chances are you have a SCADA network. A control network will have protocols like Ethernet IP, Modbus TCP, or Profinet in use on it. Control protocols that use multicast communication can adversely affect all devices on the network if not managed properly, and I'll cover that in the next slide. It is also common for SCADA and controls to be on the same network. If the network is designed and configured properly, that really is not a problem. Industrial controls protocols that use the producer-consumer model have historically used multicast for communication. Ethernet switches will flood these multicast packets to every device on the network, causing HMIs to slow and drives to drop off the network with communication errors. For networks that use this producer-consumer control protocol, use managed Ethernet switches and make sure to enable Igmp snooping. Igmp snooping will switch those multicast packets from the producers, which are the VFDs, servos, and I/O devices, to the consumers, which are the PLCs. This will improve the response time of your HMIs. There are also a lot of slow industrial networks that can be improved by simply enabling Igmp snooping on the switches that currently exist on the network. If you are using a control protocol that is the client server type, like Modbus TCP, then Igmp snooping is not required for that specific protocol. I'm sorry, I didn't go through the animation of those slides. But you can see that the producers will send multicast traffic to the consumers. The larger an Ethernet network gets, the more the broadcasts increase. Ethernet requires broadcasts for devices to communicate, so you really cannot eliminate broadcasts on an Ethernet network. A healthy industrial Ethernet network has between 2 to 10 packets per second of broadcasts. As your industrial network grows, you might add different IP networks on the same switch network. This usually occurs when an OEM brings in a new machine and uses his own set of IP addresses. Even though the different networks can communicate with each other, or cannot communicate with each other, their broadcasts are received by every device on the network. If one device on the new machine starts excessive broadcasts or multicasts, it affects the entire network. One way to break up or divide broadcast domains that we've just mentioned is to use a router between the different IP networks. Not only is it a way to control broadcasts and multicasts, it also allows the devices on the two networks to communicate with each other by using the router as the default gateway. The problem with the solution is each network has to have a cable run to an interface on the router. This can add costly infrastructure. This is one of the reasons why it is rarely done in an industrial network, and broadcast domains are simply expanded until the network is painfully slow. A better way to use the switches and cabling you already have in place is to configure VLANs on your managed switches. VLAN is an acronym for Virtual Local Area Network. By default, no communication of any kind will cross between the different VLANs. No unicast, broadcast, or multicast traffic will be passed between those different VLANs. If you add a router or a layer 3 switch, which is a switch with routing capability, you can communicate between the VLANs. It is a great solution for growing networks, but it can be complicated to implement and manage. This might be a good time to go see your friendly IT manager. In this example, each of the switches are used for one VLAN. But what if you have devices on the same switch that need to be separated? In this example, the managed switches can have different VLANs configured on the same switch. As you configure each switch port for a specific VLAN, you are creating, in effect, a virtual switch. In this diagram, the 3 devices on VLAN 2 can communicate with each other, but their broadcasts and multicasts will not be seen by VLAN 3. The connection between the switches needs to be configured as a VLAN trunk to allow all VLAN traffic to pass. This example shows 2 control networks, but you could also do this with security cameras on a different VLAN. The bottom line is you are utilizing one switch to create multiple isolated networks. As our networks get larger, how much effect does it have to add switches between our devices? Industrial Ethernet switches built within the last 5 years have a latency of about 2.5 microseconds. Typical control networks usually will go as low as 10 millisecond updates with the drive, servos, or I/O. For network switches to add 1 millisecond of latency to the communications path between the drive and the PLC, there would have to be 400 switches between them if you add up that 2.5 microseconds of latency. Today's modern switches are rarely the bottleneck to a network. In most cases, the devices on the control network are the reason for the slowdown, not the switches themselves. Large enterprise switches now have latencies measured in the 200 to 400 nanosecond range. Which brings us to QoS, or quality of service. Managed switches have a feature to prioritize network packets for specific devices. But of course, it has to be configured on each switch. The reality is, QoS is only needed when the network is congested, the congestion will begin at about 30% utilization of the network. Every industrial network that I have ever analyzed averages around 1% utilization, far below that 30%, where it starts being congested. And with switch latency being so low, 2.5 microseconds, QoS is rarely needed. Of course, if you have IP phones on your network, like an enterprise network would, then you would need QoS for that type of application. There are several choices to choosing a network topology. We will cover the options in the next slides, but we will use the TIA 1005 standard to help us decide which one is best for us. The star network is the easiest to configure and manage. In fact, enterprise networks like to use star topology where possible to keep the switch equipment in a centralized location. However, for industrial Ethernet networks, the TIA 1005 standard recommends that Ethernet copper cabling be kept as short as possible when exposed to environments in high electromagnetic interference or radio frequency interference areas. If this star network is in a noisy environment, it might be better to use a tree topology. In this example, we are using a commercial-grade 48-port switch that is located in a controlled environment where the servers reside. There are fiber optic cables extended to the panels from that switch that contain switches and the control equipment, PLCs, drives, and HMIs. Since fiber is immune to EMI and RFI, and you can have runs as long as 70 kilometers, though most fiber run within a building is using multimode cable, which has a distance of 2 kilometers. The switches in the panels are industrial grade so that they have extended temperature ranges and use the same 24-volt DC power as the other devices in the panel. This topology follows the TIA 1005 standard to keep the switches as close to the devices as possible. This example is a combination of SCADA and control, so all the switches should have Igmp Snooping enabled. But what this topology is missing is media redundancy. If we add fiber or copper cables between the panels, we can create a ring. So if one of the cables, connectors, or Ethernet ports fail within that ring, the network traffic will still pass over the redundant link that we put in. There are a few rules that need to be followed with redundant Ethernet connections. One of the basic rules of Ethernet is that loops are not allowed. If a loop is created, a broadcast storm will start and will use up all the bandwidth on the network within a few seconds. All of the green activity lights on the switches will go solid, and none of the devices will be able to communicate. The Rapid Spanning Tree Protocol, or RSTP, was created to allow loops or rings in Ethernet by controlling these redundant links, and it does it automatically. Managed switches have the RSTP protocol, which detects redundant links and automatically blocks the traffic. When one of the connections fails on the ring, Rapid Spanning Tree detects this and unblocks that port to allow traffic to pass on its redundant connection. That's what's called the heal time. RSTP's heal time is 2 to 3 seconds. The 2 to 3 second network blip isn't a problem when checking email or surfing the web, but control protocols will time out in 120 milliseconds or less. That is why many industrial switch manufacturers have their own proprietary protocol with ring heal times that are under 30 milliseconds. What no ring protocol can compensate for with this topology is if there are two failures on the network. When you start thinking about network redundancy, the solutions seem to have almost no end. For example, in this example, if the 48-port switch fails, the entire system is down. Well, how do we prepare for that? We could use a redundant star topology. If your application and budget says yes, you can add another 48-port switch and provide more network redundancy. Then you can add more media connections between the switches and use the multiple network interface cards on the servers to connect each of them to a different switch. This example uses fiber for the redundant switch connections, but you can use copper without affecting the heal time. In essence, you are creating multiple rings between the switches in case one of the switches in the server rack, one of those 48-port switches, in case one of those fails. This is great for process systems where a controls failure in the middle of the process might ruin the whole batch. In summary, I just want to touch on a few of the points that I believe are very important. Use the TIA 1005 standard to select the proper infrastructure for your industrial Ethernet network, and make sure to document your network in detail. If you have a control network with Ethernet IP, make sure you use managed switches and enable Igmp Snooping. And finally, consider your application when determining the cost effectiveness of network redundancy. So I just touched the surface with this information, but I hope it helps point you in the right direction. Thanks, and now here is Mark Hosky.
Great. Thanks, Mike, for your explanation of Ethernet technologies and recommendations for implementations. Listeners to the live Q&A can submit questions anytime, and those listening to the archive version should stay tuned for the Q&A session at the end of the presentation. I'm going to continue now offering some research results related to Ethernet from control engineering and from other sources. Here's a bit of our introduction and methodology for doing our research. We performed research to better understand Ethernet and how it helps users of automation, controls, and instrumentation. Results were gathered in October from 200 respondents. The research summary here will focus on the Ethernet portion and leave most of the mobility and wireless information for another day, even though an industrial Ethernet backbone can also support mobility and wireless applications. The Ethernet portion of the survey covered products specified, future spending and productivity resulting from Ethernet use, products and services, servicing and integrating, where Ethernet technologies are used in the workplace, Ethernet protocols, how integrated Ethernet is, how easily it was implemented, Ethernet adoption benefits, and Ethernet adoption challenges. Products most commonly used, purchased or specified or expected to be within 12 months among respondents were switches, wire or cable, networks, connectors, and routers. Other products include cord sets, gateways, Intranet structure and hardware, software, along with services. %40 of respondents expect to spend more on Ethernet in the coming year, and 40% expect to increase productivity. Also, around 40% expected to spend about the same amount and get the same amount of productivity. Just 6% will spend less, and just 4% expect less productivity. Thus, we can see that spending on products and services for Ethernet and productivity are closely correlated. Around 60% of what was spent on Ethernet goes to products. Services get somewhat less. Operations, or engineering and business IT, were evenly split among those working on, servicing, or integrating Ethernet devices. Operations, or engineering, and manufacturing IT together account for about half of the servicing and integrating for Ethernet devices. System integrators work on about 14% of the projects, and consultants help with another 4%. As a whole, Ethernet, industrial mobility, and wireless technologies are used 77% on the plant floor or operations, and about half are using these technologies while reaching into the enterprise. More than a third of respondents also use these technologies in other company locations, customer locations, or at home. An Ethernet protocol, as you may have gathered, is the software that runs over the Ethernet physical layer. Most used Ethernet protocols, according to respondents, are Ethernet IP, TCP IP and UDP, Modbus, TCP, Profinet, and EtherCAT. And you can see how other protocols play out there at present among respondents. 46% of respondents see Ethernet as highly integrated with controls, automation, and instrumentation, and 40% see Ethernet as somewhat integrated. Just 12% said Ethernet is not very integrated, and only 3% said it wasn't integrated at all. Clearly, Ethernet has become part of the fabric of controls, automation, and instrumentation for most survey respondents. Most respondents, 42%, said Ethernet was easy with plug-and-play capabilities. 37% said it's more challenging, requiring some configuration. 14% noted some difficulty, and 8% had a rough go of it, gave up, or required help. Data access is the greatest benefit of technology implementation for Ethernet by a wide majority. 63% responded as data access being the greatest benefit. Ease of use and productivity gains were cited by about 37% of respondents. Other benefits rate in the double digits, including cost savings, time savings, better asset management, less downtime, more effective maintenance, more accurate decisions or processes, greater accountability, and greater security. What stands in the way of wider adoption of Ethernet technologies? Security and lack of training and education rank highest, followed by budgetary concerns and lack of use cases, and lack of a strong business case to support the investment. At this point, I'd like to ask the viewers listening live to consider sharing their primary concerns about Ethernet in comments or questions using the interface provided. In summary, for our control engineering research on Ethernet, the most common products were switches, wire or cable, networks, connectors, and routers. 40% of respondents expect to spend more on Ethernet and increase productivity as a result. Around 60% of what's spent on Ethernet goes to products. Services get less. Operations or engineering and business IT were evenly split among Ethernet workers. Ethernet, industrial mobility, and wireless technologies are used 77% on Plat 4 and operation areas. Most used Ethernet protocols are as shown. 46% of respondents see Ethernet as highly integrated with controls, automation, and instrumentation, and 40% see Ethernet as somewhat integrated. Most respondents said Ethernet are relatively easy to install. Data access is the greatest technology benefit of Ethernet, cited by 63% of respondents. And security and lack of training, education, and support are among adoption challenges. Okay, at this point, we're at about 45 minutes into our presentation, and we're going to go on to the end here where we have our Q&A session. So let me scroll down to that next slide. And here is a little bit about submitting questions and the exit survey and archive as we go. So we're done with the formal presentations as they are, and this is the part of the webcast where we take your questions. So stay with us if you're watching the archive. The Q&A is very educational as well. Type your questions for the presenters today in the Ask a Question box on your screen, and we'll get to as many of the questions as we can. Questions will be answered verbally during the Q&A session. Within a few days, this presentation and the Q&A session will be available for on-demand viewing. If you registered, we'll send you an email when it's ready, and you can also access the webcast via the Control Engineering homepage. Now we'll go on to our questions. So Mike and I are ready to take the questions. I'll go over the questions as presented, and hopefully Mike will be able to answer the technology questions, and I can answer the ones related to the marketplace if we have any. So Mike, we'll get on with the first questions here. Make sure you unmute your phone, and we'll get on with it.
Okay.
The first question is, please provide some design implementation and protection tips related to the setup of an Ethernet network.
Yeah, I think we covered some of that when talking about the TIA 1005 standard. You know, if you take an IT person and ask them how to set up a network, they're going to take large switches and put them in a centralized location and have long cabling runs out to the control panels or the devices on the shop floor. And the 1005 standard kind of turns it back to the way it was and says put small industrial switches in the control panels or near the devices, and then have the cables run between the devices and the switches in those panels, the industrial switches, and then run fiber or shielded Ethernet cable back to a switch if you're going to a server room somewhere or a server rack. But that 1005 standard does kind of change up the thinking about how to design and implement that network. And as far as protecting your network, this is becoming more of an issue with external access required and SAP data that wants to get sent up to the enterprise side. Use a router or a firewall to protect the network. And it's always as good as whoever is configuring that device. So make sure it's configured properly to protect your network.
Great, thanks, Mike. Another question coming in. We have explain some of the differences between managed and unmanaged switches, shielded versus unshielded cable, and Cat5e versus Cat6. I know you went over some of that, but sometimes comparing one to the other is helpful. Sure.
When Industrial Ethernet first started out, most of the switches were unmanaged. This was about 10, 12 years ago. They still sell unmanaged switches, and they work just fine. The issue is you're kind of stuck with troubleshooting on a network or your control protocols that you're using. So let me give a couple of examples. If you've got a SCADA network, which you've got some HMIs that are getting information from the PLCs, and that could be that would be considered a SCADA network, you can use an unmanaged switch for that. But if you're using a control protocol over Ethernet, you would want to use a managed switch. The other thing is, if you're having a problem on your network and somebody needs to go in or you need to go in and look at the switch, you can only do that with a managed switch. And what a managed switch does is it will keep error counters for each port on that switch. So you can go in, if you have a problem, you can go in and look at the web interface for that switch, and it will tell you if you have errors on a port. Now, a lot of those metrics may not mean much to you, but all you have to do is Google up that metric, like FCS errors or frame check sequence errors, things like that, and it will tell you basically what your problem might be on the network. Shielded versus unshielded cable.
Mike, just one comment.
Yeah.
There is a security question versus managed versus unmanaged, right? I've heard that managed is better for security in general.
Right, exactly. So there are a couple of security things you can do with that. You can take the unused ports on a managed switch and disable those ports. You can also do what's called, which will lock out a port. If somebody unplugs a device from a port and they try and plug in, let's say, their laptop or something like that, it locks the MAC address of that device to that port, so it won't let any new devices connect to that switch. And also VLANs are a way to protect your network in a minor role, I guess. So then, yeah, shielded versus unshielded cabling. If you have an environment that's high in EMI or RF, I'm thinking like aluminum plants, or if you're running cable within a control panel that has a lot of VFDs, or you're in an MCC, I recommend, and also the TIA 1005 recommends using shielded cable, shielded copper cable. And if you're doing long runs of cabling, or you need to do a long run of cabling that's in a noisy environment, you may even consider going to fiber cabling. If you're within a plant, you can use multimode fiber cable, which will give you a distance of 2 kilometers. And it's absolutely immune to any noise out on the shop floor. And then Cat5e versus Cat6, I wouldn't recommend using Cat5e at all anymore in the industrial environment. I would use at least Cat6 or better. In fact, a lot of Cat6 cabling now, what they did was the cable manufacturers kind of skipped to Cat6a, and they improved it, and they took those old Cat6a type cables, and they're actually using them as Cat6, so they're kind of backfilling that category more. There are very good cables, so I would recommend at least Cat6 and maybe even Cat6a if you're putting in new cabling.
Does it matter which Ethernet protocol is used, and are there user groups available to help with that? I know for a fact that there is a user group for almost anything, and that can be easily searched on the internet. And then the user groups do provide some measure of how fast their protocol is. Can you add to that at all?
Right. Yeah. Exactly. If some of the more commonly used control protocols in the at least in the U.S., would be Ethernet IP, which is a multicast type protocol. They are moving
that's
over.
what the survey results showed that we did. That one came out on top, but certainly there are others as well being used. But go ahead.
Right, absolutely. So if you're using Ethernet IP on a network, you definitely want managed switches, enable Igmp snooping on them. If you're using something like Modbus TCP, then you can use unmanaged switches if you want to. I would still recommend managed, but you can use unmanaged switches because it doesn't use multicast traffic. Profinet is another story. There's 3 different levels of that network, I believe, and it really depends on which one you're using. It really defines which switch then you'll have to use.
And let it be said that there are effective uses of industrial Ethernet using all of the protocols that were listed. It's just a matter of picking out what works for your application and which devices are available with those particular protocols or compatible. Right,
exactly. Yeah, that's a great point, Mark. The protocols, a lot of times you may have to dig for it a bit, but the protocols will tell you, this is what features are required on the switch. You may not need all of them, but it's a great starting point. And talk to representatives who know those protocols in depth, and they will say, yeah, you absolutely need this or that feature on a switch. And once people say you need a feature on a switch, that means you need a managed switch.
Very good. There were a lot of questions that revolved around security. Do you have some tips about industrial Ethernet security?
Sure. We talked about switch level security, which is disabling ports that aren't in use, or MAC security, which will not allow anyone to connect a new device to the network. So that's switch level security. Then there's router and firewall level security, which would be the connection between 2 or more different networks. So if you've got an enterprise network that needs to communicate to your industrial network, a firewall is a great solution for that, because you can limit the traffic or the source devices and what they can connect to on your network. What it also does is it does 2 things also. It keeps your multicast traffic, if there's any that is uncontrolled, from leaking into the enterprise network and causing them problems. But on the other hand, it also keeps the enterprise systems from trying to update, Windows-based HMIs or something like that and causing a problem on your industrial network. So I think a firewall or a router is a great solution for that type of security on a network.
Great, thanks. Just one more. Could you explain the differences between a router and a switch, and briefly explain where you would use each?
Sure, that's a great question. A switch does not route traffic, so to speak. It switches packets based on what are called MAC addresses. A switch does not care what the IP address is of the traffic going through it. It doesn't matter. But if you have 2 different networks, let's say you have a 192.168.1 network, and it needs to communicate to a 10.1.2 network, basically 2 different IP networks, you need a router to do that. So what a router does is route IP traffic from one network to the next. There are also layer 3 switches that will do that. So that's basically the difference between a switch and a router. A switch doesn't care about IP addresses, whereas a router does.
Great. Thanks, Mike. I appreciate your presentation and the thoughtful answers. We'll try to get to the other questions offline and provide a link to the answers. I'd like to close by thanking Mike Robbins, our great speaker from Tricor, for generously sharing his time and expertise